Hello, everyone. Welcome to Smarter AI with Analytical Graph Database Conference. My name is Lapidot, and today I'm going to share with you how Intuit risk team leveraged Tiger Graph to improve our AI-driven risk platform. I'm not a doctor in graph theories, and I'm also not a data scientist, but I do have a strong experience integrating graph-based inputs with ML models in real production environments. My talk today will focus on a few insights I've gathered during this journey. That's the agenda I've planned for the day, and I promised you that by the end of that session, you'll have a good understanding of how to overcome some of these challenges using graph insights with ML models. Feel free to stop me during my talk. Really just burst into my talk if there's something you want to ask. And don't worry, as a born and raised Israeli, I'm used to interruptions from all kinds. After a missile alarm interruption, everything else seems reasonable. And again, we'll have also time at the end for Q&A, because I'm not sure you're able to actually ask questions during my talk. Before we dive into the main topic of my talk, let me give you a very short intro to how Intuit became an AI-driven expert platform. Intuit built an amazing ecosystem over the past 4 decades. Yeah, you heard me right. Intuit was founded in 1983. Intuit offers a wide range of products, serving small businesses, self-employed, and consumers. Our North Star is to power prosperity around the globe. How we do it? By helping our customers putting more money in their pockets with no work required and in complete confidence. The last part of complete confidence is where my talk will focus today, because more confidence means less risk. And when it comes to risk, my team and I are obsessed with how we can improve our risk prevention capabilities. Intuit's mission to become an AI-driven platform is a challenging mission to achieve. And today I want to share with you how we overcome some of these challenges that any company adopting AI will be facing. In addition to the move into an AI-driven platform, Intuit also decided to pursue graph technology for various use cases. Over the next 15 minutes, I'm going to share how we use graph technology for fraud detection, and more specifically, how we combine graph insights with Intuit's ML models to make our platform a trusted place for our customers to transact and manage their finance. Let's jump right into the challenges of combining graph insights with AI. And after, we'll take a step back to give a bit more context on Intuit risk platform and graph-based features in general. Intuit shift to an AI-driven platform basically means that most of our risk mitigation controls are based on ML models. In addition, we've implemented a graph database system to reflect our customer relationships and detect suspicious relationships patterns. However, when we wanted to combine these ML models with graph-based inputs, we faced 2 main challenges. One, when you write a graph-based policy, such as find a link between entity A to entity B in max of 4 hops, that's a very simple logic to implement. And you only do it once. But when it comes to ML model features, you need to allow data scientists the ability to explore, experiment, and develop features in the most agile and efficient manner. Tiger Graph chose GSQL as the query language. Martin just mentioned it earlier. That's not a very complicated language to learn, but also not a very common one. And that was our first big challenge: how to enable data scientists the exploration and development of graph-based features without the need to learn GSQL. The second big challenge we faced was, once you've developed the feature, how can you produce historical feature values to train your models? Our graph is constantly updated, and in order to train models using graph-based features, you need to reflect the relation status as it was at any given point in time in the past. How we achieve that? That's exactly what I'm going to share with you today. I wish I had that knowledge a couple of years ago. It would probably save me a lot of time. But by walking you through these learnings, I hope I can save you that time and help you implement graph-based features much faster and more efficiently. Before we go into the solution of these challenges, let me give a bit of context on how Intuit leverage graph technology for risk management. This is how our risk platform integrates with graph database technology at a very high level. We have the data ingestion on the left side, then we support the graph with several capabilities that serves different use cases. On the right upper side, you see the manual investigation tools such as tyGraph Studio and Intuit case management tool. This is what our agent uses to manually investigate risk cases and also to support ones found as bad. Within the orange square in the middle, you see the link analysis service, which is a REST API that we use to enforce risk policies from type link between entity A to entity B. On the bottom of the orange square, you see the graph analytics environment. This is where data scientists go to explore new graph-based features and produce training data sets. This is also where I'll focus my talk today. Let me give you a short intro to what I mean by graph-based features. What are graph-based features and why we even need them to detect fraud? Majority of ML model features can be classified into three main categories. First category can be called aggregations, such as count of payments from the same device in past 30 days. Second category of features can be called ratios. Example, number of fraudulent payments divided by number of legit payments from the same device. And last category is called raw features, such as geolocation mismatch between the IP address to the zip code. However, none of these three actually refer to the relation pattern between entities. And this is where graph features come into play. What you see in that slide is a basic example for a graph-based feature. On the left side, the yellow vertex is a business account. And on the right end, you see a red vertex that signals a fraud label. In that case, we see that the business account links to a fraud label in 6 hops. So if we were to implement such a feature, we can call it link to fraud in 6 hops. And the feature value would be true, since this is a Boolean feature. That is one very basic example of a graph-based feature, which we couldn't deduce from any other source that is not a graph-based system. Let's review a few more examples of graph-based features. As always, things get more complex down the road. Here are a few more graph-based features that we can implement using graph technology. Minimum link distance. Since there could be multiple paths to the target vertex, we take the path with the minimal number of hops. Average link distance, we also check the average path distance to target. The number of paths, we check the number of different target vertices connected to the source entity. The link strength, the maximum path strength, we can assign weights to each vertex and by that calculate the strength of each path. And obviously the path to fraud, the composition of the path itself, we can query the graph to get the actual vertex types that comprise the path of link to target. These are a few examples of graph-based features, but as you can see, there are many different insights we can gain from querying a graph database. Let me stop here, see if anyone has any questions so far. Okay, Stav, are we allowing a question during the session or just at the end?
I think it's best maybe towards the end of the session that you can answer all questions.
Okay, we'll do that. So after setting the right context, let's dive into the main challenges mentioned earlier and how we came up with the solution for these challenges. This is what I describe as a classic model development flow. At the beginning, a data scientist will explore features and develop them. On a classic model, he will do that using Python or SQL to query a relational database. Once the feature is developed, we need to generate training data sets by calculating historical feature values. On the classic model flow, this is a simple thing to do, since the data already exists for any given event, and by using simple aggregations such as sum or count, we can have any feature value calculated for any point in time. The rest of the process is the same for graph-based features and for classic features. But these two initial steps are the challenges I want to focus on. In opposed to the classic model development flow, graph-based features development flow is a little bit more challenging. The two first steps are the biggest challenge. We need to allow our data scientist teams to explore, experiment, and develop graph-based features without the need to train them on GSQL syntax. And second is to produce point-in-time simulation of relationships in order to allow historical graph-based features calculations for model training and testing. Let's see how we solve the first challenge. This is how we define the first business problem. We want to allow data scientists to explore, develop, and test graph-based features without the need to learn GSQL code. Our engineering team took the challenge and decided that although GSQL is not a common syntax, GraphQL is a common one. They implemented an abstraction layer that receives GraphQL syntax as an input and translate it into a GSQL code. This worked really well, and using an open source user interface, we've implemented this functionality for data scientists to query Tiger Graph using GraphQL syntax. Once a data scientist defines a feature, develop and test it using the GraphQL user interface, he can then make an HTTP call from any Intuit service and get the feature result in real time. That was a true success story, since the team used an open source technology and implemented a solution that created a seamless integration between Tiger Graph database and a common query language syntax, enabling our data scientists exploration and development of new features in a simple and fast manner. Let's see an example. At the bottom of that slide, you can see how a simple source to target feature looks like using GraphQL syntax. Look how short and intuitive the code is. It also supports autocomplete capabilities that makes it very fast and easy to work with. The small gray square shows the result of that graph query, which are also very easy to interpret and use as an input for models. Challenge number one is solved. Does anyone has any question? You don't need to ask because I know you can't. Okay, now let's see how Intuit team was able to solve the second challenge of calculating historical graph-based feature values. In order to calculate graph-based feature historical values, we need to know what was the relationship between any two entities on the graph at a given point in time in history. This is almost like developing a time machine. When we first started designing the solution, it was clear that this is not a nice to have feature, because if we can't calculate historical feature values, we can't use graph insights with our models. With that in mind, we started brainstorming on different solution designs, some of which were, maybe we should keep a full log of all graph changes, maybe we should calculate features and store their values on an ongoing basis. Eventually, the solution was much more elegant and easy to implement. Well, at least easier than building a time machine. In order to explain the solution, let's simplify the business problem. We can refer to a change in a graph as an addition or removal of a graph edge. With that in mind, we've decided to implement a start date and end date on any edge in our graph. Let's look at the example in that slide. We have user A that changed his bank account from bank 1 to bank 2 on January 20. Now let's assume that we have a payment from user B processed on January 15 using bank number 2. In that case, user B and user A are not connected because bank 2 was only added to user A on January 20. But if the same payment happened on January 21st, then we have a link between user A to user B. In order to support these point-in-time simulations, we need to apply these start and end dates on every edge in our graph, and also implement the right logic in your G-SQL queries, so that when the query traverses through the graph, it refers to the datetime of the source entity and ignores relations that didn't exist at that point in time. This is a basic example of how we solve the historical feature simulation challenge. But there's a lot more around it. For example, do we want to remove old relations in order to avoid confusion? Maybe we want to address old relations in a different manner. How does one produce a set of graph insights without the need to manually call the graph on every event? I'm not going to discuss all these bits and bytes, but trust me, it gets more and more complicated, but also rewarding once you overcome the challenge. So we have both challenges solved. Let's see if and how graph-based feature actually improves our ML model performance. The target goal for us is always to improve. And in risk management, improve means protecting our customers without compromising their product experience. In that slide, you see a fraud detection model that we apply to detect large-scale fraud attacks. Using graph-based features, that model showed an amazing improvement in detecting 50% more risk events and also improving model precision by 50% at the same time. Out of around 600 features used by that model, the top 20 features are responsible for around 80% of the model performance. And we can see that 2 graph-based features took a significant part in this amazing boost to model performance. For us, this is a game-changing technology that we plan to leverage more and more in the future. I would like to summarize my talk and make sure you have the 2 main key takeaways that I plan to deliver. The first one is to always, but always listen to your customers. In my use case, the customers are data science team. And if they can't get their job done, then I did something wrong. In the example I shared, we had to go through multiple iterations of design sessions with the customers and reiterate over and over again until we got to the right solution. Especially with new technologies like graph database, there's a certain maturity period that you need to allow in order for stakeholders to digest and learn before they even know what they want from it or how they want to use it. In my second example I shared, I want to emphasize the importance of planning the whole process through and not just the first steps. So when you design a new graph schema and you want to use it later for inputs to your ML models, you have to think through the whole development cycle and make sure you have the right functionality to support every step in that process. In my use case, it was the ability to produce graph historical feature values for model training, but it could be any technical or business need at any phase of the process. So 2 main takeaways: listen to your customers, and second, invest in design and plan ahead. Thank you very much for listening. I hope you gained some new insights from this talk. And I think that's the time for Q&A, right?
Yes, you have a few questions in the Q&A section and also a few in the chat. So you can start with the Q&A.
Okay, so Roy is asking if the fraud knows. So the fraud is a node in itself. Yes, that's correct. That's how we chose to implement it. The reason for that was that we wanted to have some attributes available on the fraud node. Attributes like when the fraud was reported, by who was it reported, what type of fraud. You can think of different aspects that you want to include there. So yeah, that's the fraud the fraud label is a vertex of its own. Eli is asking what happens if there are multiple start dates and finish dates. Use a switch bank to bank. So yeah, in that case, we're connecting all these different bank accounts to the same business entity. It could be a user or a business entity. And we put the start date and end date for each one of them on his edge. So you can have multiple bank accounts, for example, connected to a certain business entity, each with his own edge. So you will see the start date and end date for each one of them separately. That allows you to analyze and calculate relations accordingly for each one of the different vertex types. Parash is asking, from your experience and your opinion, what are some fields that could benefit from more graph-based models data? I believe you were asking in general, like I described fraud detection, and you're asking for other types of industry. I'm not sure if I got the question right, but the way I think about graph database, you can kind of do a analogy for, let's say you have a picture, right? 2 dimensions picture. So you can join another picture and create a panoramic view, right? I kind of compare that to a relational database. Now, once you have a graph database, you can create 3D views, right? You can see different depth of views into entities relations. That could serve you, I believe, in almost in every aspect of business and security and everything else, because it's a new dimension, right? That's how I look at it. So I think every field of data and knowledge can benefit from graph database. Why not Neo4j? Good question. We've compared a couple of technologies. I can't mention which we did, but eventually we chose TigerGraph mainly for performance. And because they were the best fit for our needs, but I'm sure others can find different pros and cons for other technologies. Is there another requirement to historical data rather than the dates? For example, some bank properties like name, size, etc. How are those managed? Yeah. So other than dates, so start date and end date are important to understand when the relation actually occurred. But if you have, in some cases, we have attributes. Let's say you want to know what's the status of a specific account, okay? Now that status is reflected as an attribute on the vertex and not as a vertex of its own. In that case, you need to maintain some kind of a log outside of the graph. This is how we solved for it, so that you can generally address and find the correct status at any given point in time. But that requires some additional implementation, and I can discuss only this topic for probably half an hour. But if you want, we can connect offline. Could you throw some light and insights on the infrastructure required to host reasonable production environment? I'm afraid that's probably more of a technical question to our engineers. So sorry, but less my realm of expertise. If you want, again, we can connect offline, and I can connect you with, or someone from TigerGraph can help you with that.
Yuri, we'd be more than happy to take those questions. Thank you.
Yeah, definitely. Is there any white papers on the cost versus performance comparison of graph versus NoSQL? again, for us, the performance is not something that can even be compared between a relational database to a graph, because the what you saw as a 6 hops of relations that I just showed in the example, you need to understand that each vertex in that path has like hundreds of millions of IDs of vertex inside of it. So it would mean joining hundreds of millions of records in a relational database that will never return a result. However, with a graph database, it comes back in less than a second. So it's not even comparable in that sense, because it's a different technology and different use. That's from the performance point of view. As for costs, you'll need to contact Tiger for that. Scope of DBA in the graph database, what is needed to know, learned, and any extended topics to be learned. So yeah, there is some learn curve, and although Tiger has a very detailed guides and they provide great support, still there's some maintenance work required. Again, it also depends on the organization, infrastructure, so different elements of restacking and how you maintain your databases. But in general, yeah, there is some learning curve here. Not too big, because again, there's a lot of support from Tiger, and basically it's more or less similar to other databases types. Do you have any more questions? My pleasure.
Hi, Uri, you have in the chat 2 questions.
Okay. Can you read me these questions? Sorry.
Yes. The first question is challenge 1. Do you use 2 layers of data, test/prod base, set and real set? Did it change the way you or the data scientist verify your ML algorithms?
So do you use 2 layers of data, test and prod, based on the real set? Test prod, you mean like, I'm guessing that you mean environments, like development environment and production environment. So yes, definitely we do. And yeah, that there's some challenge of, it's not a big challenge. You can create automation processes to produce test data according to your test use cases. Did it change the way you or the data scientists verify your ML algorithms? Yeah, so based on my talk earlier, yeah, it definitely is, because calculating historical features for non-graph-based features is much easier than doing that for graph-based features. So it did change the way we verify our ML models, but not at the end of the process, because eventually when you verify your models, you measure, precision, recall, and this hasn't changed at all. The only thing that did change was the way we produce these features and how we integrate them into our ML model environment and make them available both for training and for real-time calculations.
Another question is point in time, at what resolution? Milliseconds, nanoseconds, seconds based on epoch?
Okay, so we don't use seconds at all. I believe, sorry, seconds we do use, but not higher granular, not lower granularity than this, because eventually it depends on how you populate your data into the graph. So if your graph is loaded in real time, meaning streaming, then maybe you'll need milliseconds or nanoseconds, depends on the time you load the latency of your data into the graph. If it's real time, then possibly yes. For us, since the data is not loaded in real time, but more like near real time, so the point in time resolution didn't have to be so accurate up to milliseconds.
Looks like that's it.
Okay. Thanks, everyone. You're more than welcome to approach me either by asking Tiger for my contact details or via LinkedIn. I'm available for any other question.
Yeah, and again, our thanks too. Please feel free to contact me. That's my email's on there, martin.darling@tigraph.com. Be happy to answer any questions or provide any follow-up that's required. But thanks everyone for taking the time today to attend. And thanks, Yuri. Much appreciated.
Thank you.